So welcome to this video. In this video, I'm going to talk about some relationships between various variables in an equation or a formula. And so there's some key things that I would want to discuss. So for instance, linear and nonlinear relationships, and then direct and inverse proportions. So I'm going to come back to what it says there on top. So identify if the relationship between the variables is, and then it gives you numerous options here. So there are some options. So only linear, so that's one option. Only nonlinear. So of course we have to know the difference between linear and nonlinear. Here is the next one, which is linear and a direct proportion. Then after that one, we have nonlinear and a direct proportion. So I'll talk about that actually kind of in the beginning to exclude this altogether. Linear and an inverse proportion. All right, so and again, I'll talk about that as well. And then finally, nonlinear and an inverse proportion. All right. So before I tackle these examples, let's take a look and kind of do a little bit of a review. Linear. So there are different definitions actually of linear. All right. So what I'm going to say first is this. So the linear that typically most people will consider is when you have some kind of a formula or a function, relationships, between different variables. If it is linear, it can be placed in basically this particular format. For anyone who has ever studied kind of lines in two dimensions, you notice that this is the relationship between y and x. The m actually stands for slope, and then b stands for y-intercept. All right. So if you haven't studied that as of yet, you can certainly study it, or maybe you will study it in the future. But for our purposes is if you can create a relationship between two variables, now they don't have to be y and x, okay? So they can be a and, for example, z or something like that. But if it can be put in this form, then it would be considered as linear. Now, a direct proportion is actually a very special case of this. And most of the time, so what will happen is, if this b is equal to 0, then all you're going to have is just a scaling by the slope, which most people, for direct proportions, just simply say k because it's a constant, so instead of using m. And for those direct proportions, I'll put a link up above to a little bit longer video if you are interested in direct proportions and kind of understanding that, so scaling things. But notice that a direct proportion is clearly linear because all that has happened is that we said b is equal to 0, so we kind of have this format with this is equal to 0 there. All right, so that is a must, which brings up the point where, so funny enough, here when you're reading these and it's highlighted, notice it says nonlinear and a direct proportion. So here, nonlinear and a direct proportion. That's not possible. If it's a direct proportion, it is automatically linear. So this, okay, is false just by statement. You cannot have nonlinear and a direct proportion. So keep that in mind. So that means none of the ones that we will have will be nonlinear and a direct proportion. Now, an inverse proportion. So how does an inverse proportion work? So direct proportions is basically scaling. If one variable, so if x scales, let's say by 2, y will scale by 2. All right. If it scales by 5, y will scale by 5 because it's directly growing. Now, inverse proportion, that the opposite happens, meaning that if one is increasing by 2, the other one will decrease by 2. All right, if one increases by 5, the other one will decrease by 5, or vice versa. If one decreases by 2, the other one will increase by 2. So that's what will happen. And for those, so what we have is, so let me maybe label this. So this was direct proportion. So that's basically when they look like this. Okay, they can be written out like that with some constant. Now for an inverse proportion, it can be set up in exactly or very similar way, except inverse means that now the x, instead of being in the numerator, okay, it's right there. That is considered, if you can write a formula or an equation or relationship of some kind in this form, notice the inverse, okay, because this is in the denominator. So if it scales by 2, the other one will decrease by 2 and vice versa. So that's inverse. Now compare this inverse to the equation of linear, meaning y is equal to mx plus b. So linear means it's a line. Well, an inverse does not look like that at all because the x is in the denominator. So inverse, right away, this relationship is non-linear. So that's something that you can think about. So if I go back here, so notice here, we said that nonlinear and a direct proportion cannot happen because direct proportion is always linear. Now, for an inverse proportion, so this one right here, kind of in this pale violet highlight, where it says linear and an inverse proportion, impossible. Inverse proportions are nonlinear. If you would graph them, you would see that they're not lines, all right? And I would encourage you, you can try to graph it and see what actually happens, okay? You can take that. So that is kind of an introduction to these. So basically what we have is we have direct proportions, we have inverse proportions, we have linear, and then we have nonlinear. So if you cannot put a formula or some kind of a relationship in this linear form, it means that it is nonlinear. All right? So that's what it would mean. So let's use this and try to see it with some examples. All right. Now, if you're thinking about linear, it always means some kind of a line. So what I'm going to do is let's take the first example right here. Copy it and paste it. So this is a formula and it has more than just 2 variables. It actually has 5 variables in here. And now, okay, so what it says is the following. It says we have P times V is equal to nRT. And it says we want to be able to see, okay, what the relationship is between P and R. So one of the first things that you can do to help yourself is solve for one of them. And you can choose whichever one. So it says P and R. So I'm going to be solving this for P first. So isolating for P. So if I isolate this for P, so if I divide both by V, I'm going to get P is equal to N R T all over V. That is just rearranging this. Now, my question is, I want to have a relationships between P and R. And notice, when you say that, you are assuming that all the other variables are constant, meaning that they are not changing. If they're not changing, you can think of it as just as a number. They're just some number. So let me give you an example, because for anyone starting, this might help you initially. So because they're constant, so let's just imagine, and you can pick some arbitrary number. So I'm going to say n is equal to 2, t is equal to, let's say 3, okay, and then I'm going to say v, all right, is equal to also 2, just for convenience. So they're constant, meaning they're not changing. If I would substitute that in, I would get 2, right? So I have my r. T would have been 3 all over 2, which would have been my v. Now, that means I can actually compute this, right? Because 2 times 3 is 6, and 6 divided by the 2 is 3. So my equation, or my new formula, would have looked like this. Now, in general, because they're not actually, n is not equal to 2, and t is not equal to 3, or v is not equal to 2, this is just to show you. Okay, in general, you would have said they're constants. Now, if I would multiply them, I would have some number n multiplied by some number t divided by a number v. So what I would have had is I would have had n multiplied by t divided by v. Okay, that would have been just some number. This would have been a constant k. All right, so your equation would have looked something like this. And this now should ring a bell, right? And so notice here, if you use numbers, you would have had this. If you use just constants, it kind of looks like this. And now the question is, what does that look like? So from the ones we described, okay, is it a proportion, meaning direct? Is it an inverse proportion? Is it linear or non-linear? So now you have to match it. Notice that this basically looks like a direct proportion. Direct proportion. The p is kind of like your y. The 3, okay, is kind of like your constant, and then the r is like your x. So it is a direct proportion, and we know that the direct proportions are also linear, right? So the relationship between p and r, if we were picking from here, from the list, okay, so it's not only linear, because it is linear and a direct proportion. That's the one we would have picked for this particular example. And that's how you would kind of show it to see it for yourself. So it is a little tricky, and you have to be able to understand, okay, how these two relationships work. So let's look at another example. So I'm going to say, so this one right here, let me copy it down. Hopefully it copies correctly. Let me paste it. So again, so your first step is, so now we want to be able to, what is the relationship between these two? So you have to solve for y, or you have to solve for z. All right, so you can solve for one of those variables, okay? And try to find relationships. And all the rest, so meaning the x you can assume is just some number. Now I've actually solved for y already, okay, in a past video. I'm going to put a link up above if you want to see it, or you can try to solve this on your own. And when you solve this on your own, what you should get is this relationship once you solve for y. Y is equal to 2x all over, okay, z plus 4. Now, the x is like some number, right? It's constant, it's non-changing. And here our relationship, notice the y and then the z. Now the z is in the denominator. So you might get tempted and say, this looks kind of like an inverse proportion. The problem is that inverse proportions look like this. They have something on top, which is just one item, and only the variable at the bottom. And here, we do not only have the variable, we have the variable plus 4. And that does not match, so it does not match this. So it cannot be an inverse proportion. It cannot be a direct proportion, because direct proportions look something like this. It cannot be linear, because again, linear would look something like this. All right, between the relationships between your variables. So if it's none of these, that means that this relationship is only nonlinear. That's what we would have here. That's for this example. So this is only nonlinear. Let's take a look at another one. So this next example, so here we have it. All right, copy. Paste. So now here, what we want is we basically want to be able to see what the relationship is between R and between D2. Everything else is just a number. Okay? So fine. So let me rewrite this. So I have R because it's already set for R. Now it says everything is a constant. So this right here, you can assume that D1 is some number. So that's going to be some constant, let's say K1. All right. Now this TP is also some constant. So it's just some number. So it's like saying that I can take these and just multiply them together. So there would be just two numbers multiplied together. So it would have looked like K1 times K2 would have given me some K. And in here, I would have had 1 minus D2. All right, so it would have looked something like this. And now this relationship, if I expand into the brackets, so notice what happens. You're going to get K minus KD2 R. And now, what does this resemble? So first, is it a direct proportion? No, because we have a K there. All right, so that K in front, remember, a direct proportion should look something like this. There shouldn't be anything else added or subtracted. So this, at the moment, so I'm going to rearrange this, is going to be minus K D2, all right, plus K. All right, so it looks something of that. So I have some number, so in here, and then some other number there. So that can't be a direct proportion. It cannot be an inverse proportion either, because my variable is not in the denominator. Now, is this linear? Remember, linear means that it should look something like this. It's something in front of the variable plus some b. Well, it does look linear. So this is your m. This kind of looks like this is your x variable, and this would have been your b. Okay, and your r is your y. So it turns out that this relationship, the way that it's set up, assuming that d1 and tp are just constants, so this would have been only linear. That's what this would have been. Only linear. That's that relationship. And these are not easy concepts at all to try to understand. And yes, you probably will be frustrated in the beginning when you're doing this. So you have to be able to practice this and try to understand, okay, what is exactly happening here? So that's that example. Now let's take a look at this next example. So I'm going to copy this. All right, so for this one, we want to be able to see the relationship between f and delta x. So here's delta x, this is f. So this, you can kind of see, so if you would have this is your y, all right, this is kind of like your slope, m. This would have been like your x. So notice there is really no intercept, so there is no plus b anywhere here, so that is 0. So from what we've discussed, this one is a little bit easier, and this is a direct proportion. So this is direct proportion, and of course direct proportions are always linear. All right, so that's what we would have there. Okay, so that's this particular example. Now next, so the last example that we have, which is this one, let me copy. All right, let me scroll it down. So this is what we would have. Now we want to be able to see the relationship between these two. So it's already, so here's my g, and then my G1 is right here. All right, so this one might be a little tricky, okay, to note. So what I like to do is we're assuming everything else is constant. So it's just some K. Okay, so let me rewrite this so it cleans it up a little bit. So this is what it means. Okay, so I'm going to assume W1 is some constant. All right, so it's some constant K1. G1, okay, is what I am trying to relate it to, plus. Now, these two are constant. So that means I can multiply them. It's like I'm assuming I know the numbers. So it's just some number that I have. This would have been like constant K2. And you can put numbers in there if you like to make yourself, think, okay, it might be a little bit easier to see. And then in the denominator, because W1 plus W2 are constants, so they're just some numbers, so that would have been some number K. And now with this, so I have G is equal to, so it would have been like K1 over K3 G plus K2 over K3. Again, these are just constants. All right, so these are just constants. There's some number. All right, so that's what I would have had. Now this is G1, let's not forget. So if I'm looking at this, this looks very much like y is equal to some constant. This is your m. This would have been like your x plus your b. So this relationship looks like it's only linear. All right, so it's not a direct proportion or an inverse proportion. So these are some examples, definitely tougher examples. I'm sure that you're going to be struggling with this concept. So the relationships and formulas to know if things are direct proportions, okay, inverse proportions, or if they're just linear or nonlinear is kind of useful to know. All right, because we want to be able to know what happens between two different variables or sometimes two different quantities. Okay, so thank you for watching. I'm sure that there might be some questions related to this. All right, good luck and go over this as much as you possibly can so that you slowly understand this concept. Okay, bye everybody.